Okay, so let's look at this problem. So what we have a cantilever B. You'll notice we have a fixed connection at A. It's free at B. And I want to find the shear force and bending moment equations as a function of x. And I've indicated x. You can make the coordinate system wherever you like, but I'm going to try throughout the course to always start at the left and have it go to the right. So we're going to use method of sections. So at that distance x, I'm going to imagine a cut in my structure right there. And we're going to talk about what I would need to do the right-hand side and what I would need to do the left-hand side. So let's talk about the right-hand side. Is there any advantage to doing the right-hand side? Well, B is a free point. There's no reactions there. So I don't have to find any reactions to get started. The disadvantage is it's trapezoidal. I have to do a little more work. And also, what would this distance be as a function of x? 20 minus x. So what you might see now is that when you do your method of sections in some moments, this will be a little more tedious to deal with instead of just x. So I'm going to decide today that I like the left-hand side better. It's a triangular model. That's easier for me to deal with. It's just x, not 20 minus x. But the disadvantage is I've got to find my reaction moment today. So let's do that. Now, since I'm writing equations for shear force and bending moment, I'm going to come over here to A, and I'm going to say, what is a positive shear force at A? Would it be up or down?
Up.
I've heard both answers. It's 50-50. What does positive shear force do to that edge? Does it make it rotate clockwise or counterclockwise? Clockwise. So it should be up. So this is the positive shear at A. What's positive bending moment on this edge look like? Clockwise or counterclockwise? Clockwise. Positive moment at A. We don't care about axial force, so I won't consider it. Is everybody comfortable with that? So these are just not a reaction force and a moment. This is shear force and bending moment. So I'm using the positive sign conventions for those. So now I'm going to solve this entire free body. To do that, I'm going to need the concentrated equivalent of the distributed load to make it easier for me. It's a triangle, so it's going to be 1/2 base times height, which looks like it's going to be 20, right? And what's the distance from A to that location? Well, on a triangle, it's 2/3 from the small end or 1/3 from the big end. So 2/3 of 20. I'm just going to write that as 40/3. That way I don't have to worry about computing a fraction right now. I'll just leave it in fraction form. You see that? 2/3 of 20, 40/3. Everybody get that? 2/3 times 20, 40/3. It's very difficult. It's 3rd grade, I think. It's called multiplication. Right? You guys with me?
Yes.
You look dull. Is it because did I beat you on the head too hard with the report? And are you hungover from that experience?
A little bit.
Are you hungover or hungover from that experience?
Correct. From the experience.
Good answer. All right. So let's sum moments about A. That way, my shear force at A passes through A, won't create any moment. Now, I'm summing moments about A. I'm using statics. I'm saying this is my positive sign convention. So what kind of moment is this? Negative. So I'm going to have negative moment at A. About A, what kind of moment is this, the 20 create? Positive or negative? Negative. So that'll be force 20 times moment arm 20/3 feet. So what's the moment at A? It looks like it's going to be negative. What's 800 divided by 3? 266.7? I don't have a calculator, I'm just guessing. Is it? 266.6666666666. We'll go 266.7. And that will be kip feet. Now what does that mean that I got a negative moment? Well, I assume positive bending moment, so that means the bending moment at A is negative. Does that make sense? What do you suspect this beam will bend? How do you think that beam will bend? Yeah. It's going to come out here with no rotation and it's going to go down like this, right? And you can see that's kind of our frowny face. So we expect probably all the moments to be negative. So far so good? Let's go ahead and get our shear force. So I'll assume up is positive, so I will sum forces in the y direction. Make sure it's an equal. Oh, I forgot my 0 up here. You notice that? Sorry about that. So now I look at my shear. Up is positive, so the shear force is up. And what else do I have? I have 20 kip force acting down. So that's not too bad. So my shear at A is 20 kips, which means the shear at A is positive. Okay, so now I'm going to come down here and I'm going to draw my Freebody diagram for this left-hand section. As we talked before, we're going to look to the left. I'll make it a little larger so we can see it. Now, over here at the left side, what do I have? I got a shear force of 20 and it's acting up. I got a moment of negative 266 and it's behaving this way. Okay? What's the distance of this particular element? X. So I'm cutting it at an arbitrary distance x and looking to the left. So that's one big difference right there compared to what we've been doing the last couple of days. It's not 5, it's not 10, it's x. And what range can x be? What's the smallest value of x we can have?
0.
What's the largest value we can have? So x is going to be between 0 and 20. This equation is only going to be valid between 0 and 20. Now when I get the equation for x, I can put in negative values. I can put in values bigger than 20, but they're not going to have any physical meaning. Okay? So then I'll go over here and I'll draw an idea of what my distributed load looks like. So what is the intensity of the load right there at x? Well, I know. Can I figure out the slope of this line? Yeah, what's the slope? Rise over run. That's 2 over 20. That's 1/10. So this value should be x over 10. Does it work? When x is equal to 0, what's my load?
0.
That works, right? When x is equal to 20, 20 over 10 is 2. It works. A straight line only needs to have max 2 points, and you should be good. So now this tells me the intensity of this loading anywhere x. That's something new. We haven't done that before. So now I get to my edge that I cut, and I'll assume positive shear force and positive bending moment. Now, how do we handle a distributed load normally? We figure out the area. What's the area of a triangle? 1/2 base x times height x over 10. So that force should be 1/2 the base x times the height x over 10, which is x squared over 20. You see that? 1/2 base times height. And what's the distance from the centroid of the triangle to the right edge? It should be 1/3 the distance. What's the distance? X. So this should be x over 3. So conceptually, it's no different than what you've done before, except when you started off, the length of the element is variable. And that you can see how that correlates or lands in all the other different values. That's why you can see that, as I mentioned before, if you draw the correct free body diagram, I'm going to be pretty happy with you and give you most of the credit for the problem before you do anything else. So now we just apply equilibrium. So let's do what we've always done. Let's sum moments. And we're doing method of section, so let's sum moments at the cut and make sure in equilibrium. We'll use right-hand rule for the sign convention. So what kind of moment is this with my sign convention using statics? Positive. About the cut, this force creates positive or negative moment. The concentrated equivalent force creates positive or negative moment about the cut. Positive. So the force is x squared over 20, and the moment arm is x over 3. So this is force, this is distance. Then we get over here, what do we have? The reaction shear here at A creates positive or negative moment? Negative. So that's minus 20, that's the force. What's the distance? X. And then don't forget your reaction moment. That's a positive moment under this sign convention. That'll be plus 266.7. So all I do is solve for the moment. So my moment now as a function of x is yes.
Did we not make that 266.7 negative? Since it was
No. I'm assuming right-hand rule is my sign convention, and that's a positive moment with right-hand rule. Remember, this is statics, not, I didn't say bending moment, I'm just summing moments. This is a negative bending moment, but in my sign convention, it's positive. Will it all work out?